Hi there. Thanks so much for showing up for your math learning. It's Mr. Jennings, and we are looking at sinusoidal functions again, just going for a deeper dive on some of these topics, particularly if we're shown a graph, can you build your equation? That's one of the skills. Or just if I give you words or like a situation, can you build the equation from that? These are some of the things that we're looking at today. Let's go. So recall that we have these transform functions, sine of x, and we can change the period, we can change the amplitude, we can phase shift, meaning we shift where it starts, left or right, and we can move the whole thing up or down with the horizontal axis. Okay, we can move that center line or horizontal axis. And we can remember this formula that k is not the period, but it certainly is related to the period. All right? And amplitude, we're going to be looking at positive and negative amplitudes as well. So if we have our sine function, sine looks like this, but negative sine, rather than starting in the spring, starts in the same place but is fall. Okay, so this is negative sine, and it would look like that. Okay, so positive sine starts in the spring, goes to summer, goes back to fall, goes to winter, and then back to spring. Negative sine starts in the fall, goes to winter, goes to spring, finally gets to summer, and then wraps around back to fall. Okay. Cosine, on the other hand, here's positive cosine. Starts in the summer and goes down. All right. Negative cosine starts in the winter and goes up. Not really surprising there. That should intersect that spot. Like that. Okay. Let's keep going. Okay. So let's just extract the information from these types of examples. Okay, so you could pause the video here, complete the chart, and then check it against my work. You're back? Great. So we get the amplitude here from this number. So this amplitude is 1. This amplitude is 3. You could say -3, but the amplitude is 3. And here the amplitude is 1/2. It's always just the A coefficient that's out front. The period, we have period equals 2 pi over k. Okay, so here we have a 2. So our period is equal to 2 pi on 2. I can't even write it, which is pi. Okay, because the 2's cancel. Okay. Over here, we don't have a k, so our period is 2 pi. No surprises. And out here, we have a 2. All right, so our period is going to be 2 pi divided by 2, or pi. All right. Now, what if we have a phase shift? Okay, phase shift is from -d, so we are going to be moving pi by 6 to the left. Okay, because it's positive, so it goes in the counterintuitive negative direction. Okay, same thing on the next one. We have a plus 2 pi by 3. So we are going 2 pi by 3 left. Now how about this one? Be very careful. There's the trick in this slide. All right, so here, if we factor that, we need to have this factored. All right, 2 times x minus pi by 4 is the same thing as that, but this shows me clearly my k and my d. So here I go pi by 4, not pi by 2, to the right. Okay, we have to have that k value factored out of this, otherwise it messes things up and we can't see things as clearly. And then the vertical translation, this one, the y is equal to 3 for the horizontal axis. Here y is equal to -1, and here y is equal to -3. You can see that's -3 if I cover up all of my ridiculous sketchings there. Okay, so that's how we would extract that information from an equation. Now, if you're given a graph, you can just look at the maximum and the minimum and take the distance between the two and then divide that distance by 2. And that always works to give you your amplitude. Because look at this. If you knew this and you knew that, the amplitude is this. So that's literally half the distance between the maximum and the minimum. Okay. Finding the phase shift is tricky. We'll do it in examples. Like talking through it is just going to confuse you and me. Just do it. Okay. And then C, to find the vertical shift, this one, we're actually averaging this and that. Averaging that brings it all into here. Another thing you can do is just take your maximum and subtract the amplitude, and you will get the vertical shift as well. And then finally, when you're looking at period, you're just going to find the distance between two maxima, or the distance between two minima, or if you must, the distance between a spring point and a spring point, or a fall point and a fall point, and then use your formula to find the period. Okay. So if we're looking for a sine or a cosine function, or indeed a plus or minus sine or cosine, we're going to be looking for the smallest possible phase shift. Okay. So if we look at like how this thing's been shifted this way or that way, and we compare this point, spring, to how close we can get that to the initial value, that would give us our phase shift and our best way to find it. If we wanted to work from a maximum, that would be for plus or minus cosine. Sorry, plus cosine. Yeah. So anyhow, so let's take a look at this one. If we want, and this one we're going to do for all of them. Okay, so here, first thing that we're going to do is notice that this is here 4 pi. So our period equals 4 pi. All right, and that gives us, well, what's our k value then? K would equal, so the period is k is equal to 1/2, but how would you know that? Well, we can use this formula. We can see the period equals 4 pi, but that's a fancy way of saying 2 pi over k. And then we're just going to solve this for k. So if we have to solve that for k, we're going to go multiply both sides by k and divide both sides by 4 pi, 2 pi over 4 pi. Okay? Or in other words, k is equal to 2 pi divided by the period. In this case, 1/2. So there's our k value. Our a value is 10, because we have a maximum and a minimum of plus and minus 10. And that also shows me the average of plus 10 and minus 10 is 0. So this is our average. So that's our c value. C equals 0 and a equals 10. So I've got everything except for d. Okay, so let's do positive sine first. So we have f of x is equal to 10 sine of bracket 1/2 bracket x plus or minus d. Okay, we're going to leave that for a second. Plus 0, so I'm just going to leave it. All right, now I know that this is my starting point for sine, and it's back there at minus pi, and so that has been taken from here and pushed that way. So when we're shifting things to the left, that's minus, sorry, that's plus over here. So it's going to be plus pi. And that's going to shift it backwards by pi. Okay. If we wanted negative sine normally starts over there, and I can see that's been moved in the positive pi direction. So it's moving forward by pi. So since we, then we would also have this function, f of x is equal to negative 10 sine of 1/2 x minus pi. Because positive shifts, we have to have the sign flipped version in there. All right. Now, for cosine, f of x equals, I see this one starting in summer, and that's where cosine starts. So I have no phase shift necessary. 10 cosine of 1/2 x. No d value. So no need for brackets and extra stuff there. If I were working with negative cosine, this would be the least efficient function to use in this case. So we'd avoid it, but we're doing it just to practice. 10 cosine of 1/2 bracket x. And then we could go plus or minus 2 pi. Because notice that our winter is where negative cosine starts. It happens at 2 pi or negative 2 pi. So I can do plus 2 pi here. And that would be just fine. So this shows you the difference between positive and negative sine and cosine. It's all just differences of phase shift. All right, so for this one here, we can see this one's been shifted. It has a c value of -1 because that's the average of the maximum and the minimum. Okay, so we have, and then what's the maximum? Well, it's 2 above the axis, so 2 is equal to a, -1 equals c, and then what's our period? Well, go from one of the starting spots to another starting spot, and we see the period here is 2 pi by 3, and if we want to know what that is in terms of k is equal to 2 pi divided by the period, and that happens to be 3 when you flip and multiply. So we've got all those. Now, same idea, cosine. Positive cosine, that is, needs no phase shift. It's our preferred function in this case. So we would say f of x is equal to 2 cos bracket 3 bracket x, and the bracket and the bracket. We don't need all those brackets actually. Better would be like this. Cosine of 3x minus 1 will give us this function. If we wanted negative cosine, -2 cosine of bracket 3 bracket x. Negative cosine would start back here at negative pi by 3 or over here at positive pi by 3. So I'm going to go minus pi by 3 to shift that. In this case, I'm taking what would have started there and shifting it that way. Okay. -1. Now, how about positive and negative sine? Nothing else changes except for the d value. So, for positive sine, this is our most efficient phase shift. It means we want to take sine's normal pattern here and shift it all back by pi by 6, half of pi by 3. So if we're shifting to the negative direction, that means we have negative pi by 6. -1. And then f of x, the last one, -2 sine of 3 bracket x. Well, negative sign starts in the fall, and we see that that has been shifted to the right, and shifting to the right this one is positive and this one is negative. Oh dear. Okay, so let's explain these two because I clearly had just a little gap in my thinking. Okay, so with these ones, you want to think, how much has it been moved by? Positive sign would have started there and gone up, and when we're seeing things shifting to the left, that's where we have positive in there. If we have things shifting to the right, that's negative. These are, of course, great times to check your work in Desmos. So here is -2 sine 3 pi minus 3x minus pi by 6, and we see that matches the situation that we wanted to create, so we're very happy about that. And then if we were to have this one be positive and then over here this one be positive, then it's the same again. Okay, so both of those are equally inefficient, and we would be choosing cosine. All right, let's keep going. So this one is more of a meaty example, so let's talk about how we would manage this one. So first thing to gather is we could gather our a and our c first. So we see the maximum is at 3, the minimum is at -1, the average of 3 and -1 is 1. So there is c equals 1, that's our c value, and we can see that the amplitude here is 2. Okay, so 2 equals a, and we can have plus or minus 2. All right, so now if we want the most efficient one, we're going to choose the one that's closest and see how we can shift that over there. But really, to get thinking about that, we want to know how much things have been moved around by. Right? So here, what is our period? We don't even have that point there. That's super weird. Well, we've got pi by 4 and 7 pi by 12. So if you have 7 pi by 12 and you take away pi by 4, that's the same thing as saying 7 pi minus 3 pi all over 12, which again is a fancy way of saying 4 pi by 12, which is a fancy way of saying pi by 3. So this range here, from there to there, is precisely pi by 3. And that's half the period, because the other half is over there. So with another pi by 3, and we add those together, our period equals 2 pi by 3, meaning k equals 2 pi divided by 2 pi by 3, which is a fancy way of saying 3. So there's k. We've got k. All right. So now, if we did pi by 4 minus pi by 3, we'd have the x value of that point. So let's try that. Pi by 4 minus pi by 3 is the same thing as saying 3 pi minus 4 pi by 12. So that's negative pi on 12 right there. Okay. No, that's kind of interesting, because that is that's a 1/12 of the, sorry, pi by 12. If we're wondering, like, well, what is our quarter period here anyway? Because we could use our quarter period to find things like this point and that point. And the quarter period is half the distance between here and here. So this is pi by 6. So just draw your diagram and figure these things out. And then we see these are good points here. Negative pi by 3. This one, pi by 4 minus pi by 6. These are the good points that we might consider making a function out of. They're going to be the closest ones. So looks like positive cosine or negative sine are our best options to model this function. So let's get those, the x value for this one. That's going to be very useful. And we'll get that one. Why not? Okay, so pi by 4 minus pi by 6 is the same thing as saying 3 pi minus 2 pi by 12. So this is pi by 12. This is negative pi by 12. So equally efficient there and there. We're splitting the difference in the middle. And this one over here is going to be pi by 4 plus pi by 6, which is to say 5 pi by 12. So this one is 5 pi by 12, 1. So now we've got all of the things that we need to really make our function. Okay? So let's just tidy this up. That's all very rough work. I don't know why it doesn't just erase right away. It's going to do it slowly. This happens when I'm recording. Computer gets a little tired or something. So let's start with cosine. F of x is equal to, we have our a value, which is 2 cosine. That's going to be working with this one. Put it in brackets. We have k is 3. X, we're going to take it and shift it to the left. That's going to be add pi by 12 plus 1. Our c value is 1. Okay. And then if we were looking for negative sine, that'd be f of x is equal to negative 2 sine of 3 bracket x minus pi by 12 plus 1. Now let's check and make sure that we nailed the 2. And then if we use positive sign, it would be minus 5 pi by 12. And if we used negative cosine, it'd be minus pi by 4. Okay, I'm not going to write them out. You could do them, but we're not looking for those. We want the most efficient ones. Show it in Desmos. So there it is. There's one of them. And it worked. That's what we've got. So that's what we're looking for is this stuff here. And being able to do it in terms of positive and minus sine and cosine. Yeah. Okay, let's keep going. So, yeah, so there was this handout here. So this one is a more tricky problem. So we're going to continue that in just a moment. All right. So what do we know about this one? Okay, has an average value of -3. Well, let's just C is equal to -3. That's really straightforward. A minimum value of -8. Okay, we imagine it. Here's the line -3. Here's the line -8. Okay, and I imagine that this is down by 5. So the amplitude is plus or minus 5. Like, we're going to find some positive ones, some negative ones. Okay, and then here we have, this is where the maximum values occur. All right, so something cool about this is this one is plus 4 pi on 4, and this one is also plus 4 pi on 4, which is plus pi. All right, so if the maximum values are occurring there, there, and there, then the period is pi. Okay, so period equals pi, and that means k equals 2 pi over the period, which is 2. Okay, so we've got our k value, we've got our a value, we've got our c value. Now we just need to know that phase shift. Problem is, we only know about some periods that happen like over here, right? Sorry, its maximum value is occurring over here somewhere. The maximum value is going to be at 2, okay? But how are we going to figure that out? Well, just chase your maximums back, okay? And you can chase them back with the period. So I happen to know that 17 pi on 4 is a maximum, and so is 21 pi on 4. Well, it stands to reason that 13 pi on 4 and 9 pi on 4 and 5 pi. I've gotten so many I might as well just finish it. And then pi on 4. These are all maximums, and that's the closest one to the x-axis. This is the closest maximum that we'll find. All right, so that's great. Isn't that lovely? Okay, it's lovely because we now have that one. But what if we wanted a more efficient method? Well, I would just take away, I would just say 17 pi by 4. I mean, that's the same thing as saying 4 1/4 pi. And I can take away multiples of the period. So I could do like -4 pi and just get a 1/4 pi. That's my first maximum. I can just take away any multiple of 4 and it's going to be the same. So that's a more efficient way to do that. Okay, so now we know that our first maximum occurs at pi by 4. Oh, the erasing is working much better this time. Oh, I spoke too soon. All right, so we know our first max is at pi by 4. So that gives us f of x is equal to, we have an amplitude of 5. We are going to use positive cosine because our first maximum, and that's where cosine starts, is at pi by 4. So that's the point 2 pi by 4. Sorry, pi by 4 2. I dyslexic that, sorry. Pi by 4 is the x and 2 is the y. And that's our first max. So f of x is equal to 5 cosine of k is 2 x minus pi by 4 because we shift it that way. You just put that in for d. And then we have -3 for c. Okay. What if we wanted something for sine? Well, my feeling is that we have a starting point for sine somewhere back there. So let's figure that out. Sine would start 1/4 period earlier. Oh, wait, it's not back there, is it? It starts right on the line and goes up. So 1/4 of my period is pi by 4. So I can also have f of x is equal to 5 sine of 2x minus 3. No phase shift required because sine will start 1/4 period before cosine does. So that puts the starting point directly on the x-axis. So next, you just go ahead and just type these things in Desmos and verify your work. Okay, you do this while you're studying, you do it every time, and you're not surprised later on when things really are just like working out really well for you. So there's our first maximum of pi by 4, 5 pi by 4. And then if we wanted to see the ones that were talked about in the question, here they are. Those maxima that we were told about has its minima there, and its average value is y is equal to minus 3. Good. And if we wanted to check the cosine one, we had this, but we wanted minus pi by 4. And then we're still in the same spot here with these given maxima. The minima are in the correct place, the average value is in the correct place, and it didn't move the starting point, which is still there. Okay, so that's like a trickier example. Okay, and then this just gives us more space, and that's the sine function that we know and the cosine function that we know. So here, this is like a step-by-step of how you can do it. So first, draw the center line, and you can do dotted lines for your maxima and minima. So like you're going to go here, you're going to go center line, you're going to go your maxima and your minima, and that's your range, right? That's a visual representation of your range, and then you can just link up your points with a beautiful line. Determine the period and quarter period, and split the domain into the quarter period. So there's a quarter, 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 right? My period here is right there, like that. We're going to plot 5 points without the phase shift. I do it without the phase shift first, and then draw the smooth curve. Do this very light. And then apply the phase shift, and then do this in heavy. So that we see it beautifully. So if we wanted to sketch this one, let's actually do one that's a little more robust. Okay, so this one here, I'm going to do this one. So first thing I'm going to do is get my beautiful axis. I know that this is going to be a fair bit below the line, a lot of it, so I'm going to put my y-axis, my x-axis there. I want my domain to be from 2 pi to negative 2 pi. All right. And we have our c value at -1. So let's just go ahead and do that very gently here. So we have -1 down here. There's -1. Our minima are going to be 4 below that. So we'll call this down here at -5. Okay, that's -5. This is -1. And our maxima are going to be up here at 3. Okay, and then we're going to figure out just like the period here. So there we've got 1/2. So the period is equal to 2 pi divided by 1/2, which is to say 4 pi is our period. Cool. So now I would go through and figure out, well, what's our quarter period? Our quarter period is pi. So I'm going to go back here, and we have in our pi there, and our negative pi there, and this is negative cosine. So I'm going to do a very light sketch that starts there, goes there, goes there, goes there, and goes there, right? It starts in the winter and goes up to spring, and then goes up to summer. And if I go back in time, it would be fall back there, pi years ago, and then 2 pi years ago it was summer. Okay. Now we're going to finally apply this phase shift. So it's minus pi by 4, so I'm just going to shift everything to the right by 1/4 pi. So there, that's the point 1/4 pi minus 5. Okay, this one here is going to be 5/4 pi, because it's 1 plus 1/4, minus 1. Okay, and then this one, we don't have it on our graph, but I'm going to show it anyway, is it's not that. That's just me making a weird noise. It's 9 quarters pi. 9 on 4 pi. Okay, and 3. This one is 7 quarters pi, because we're going to just add a quarter pi to that. 7 quarters pi, and still at the maximum 3. And this one is minus 3 quarters pi. Sorry, minus 3 quarters pi. Minus 1. Okay, so there. Now we're going to join these with a beautiful curvy line. Interesting question would be, where does this intersect the original function? And it's only going to intersect once in the domain. Oh, sorry, twice. It'll intersect there, and it'll intersect there. But I wouldn't ask you that question. It's a little gnarly. Okay, so there. That's what our sketch looks like. And do you suppose we should check that in Desmos? Yes. Minus 4. See how quick it is to check it in Desmos? And then we knew this was, I think, 1/2. Pi minus pi by 4 looks right. Minus 1, I think it was. And we were looking at it on the domain of 2 pi to 2 pi. Okay, so there's one of them at 9 quarters pi. There's one of them at 1/4 pi. That's not in the right spot anymore. The midline is up here. Minus 1. And so we have that at 5 quarters pi and negative 3 quarters pi. So yes, all of the places that I said. Right, so this is the way that we do these things. So we did that one, and then go practice, everybody. Go practice. And when you have questions, certainly come and get me. Bye for now, everyone.